let me do one more process. So you could look at neutron, nucleon, nucleon to nucleon, nucleon plus an axion. And there's sort of a lesson here. So if you look at how the axion couples to the nucleon, it's derivatively coupled. So you have a gradient of the axion field. And there's two possible couplings that you can write down, if you just consider the sort of lowest dimension in our power counting. And this is a process that actually is important for bounding axion physics. For example, axions in the sun. You worry about how they couple to nucleons. And the thing that's actually important is if you're thinking about this kind of process, you have to decide kinematically what region are you looking at. If you're interested in bounds from the sun, you're interested in a situation where the energy of the axion is of order the energy of the nucleons, but the momentum of the axion is much less. So I'll call that K axion is much less than P nucleon. Okay? So from a power counting perspective, the energies are the same size, but the momentum of the axion, which is a relativistic particle and is comparable to the energy, is much less since the nucleon momentum is much bigger than its energy. Remember that the energy goes like p squared over m, so the momentum are bigger. And if that's the situation that you're in, then when you're doing a Lagrangian like this, you have to be careful about implementing something like that. And the way that it gets implemented is by a multipole expansion, which we'll have opportunity to talk more about in the near future. But basically what it corresponds to is that you've got to make sure that you're not, that you're sort of exchanging energy between these operators but not momenta. That's what happens at lowest order. So if you make this expansion in the Lagrangian, it corresponds to setting the spatial components of the axion field to 0. Okay, so this is like doing an expansion around x vector equals 0, and that's the same thing in position space as this expansion here. So this is implements the k much less than p expansion. Okay, so that would actually be the operator that you would use to couple axions to nucleon. Now the interesting thing about this operator, which ties into what we started talking about today, is that once you take x equals 0, the things that you're left with here are related to conserved charges of the SU4 symmetry. So Q mu nu, which is an integral over all space of n dagger sigma mu tau nu, n, that's the charge of SU4. And the reason that it's related to that is because once I take x equals 0 here, once I do the integral d4x of the Lagrangian, the time, this still depends on time, but it doesn't depend on space. So I can move the d3x through, just let it act on this, just let it act on that. And then I get Q mu nu, Q0j and QJ0 and QJ3. So this guy here, different color. It's like QJ3, QJ0. This guy here is like QJ3. And that actually has non-trivial consequences, because charges, if they're charges of a symmetry, are time independent. So even though in principle I didn't make any assumptions about the time dependence here, and these operators could exchange energy. If I know that they're related to charges of the effective field theory, then charges are conserved. There's no time dependence. So charges of the field theory are time independent. And what that means then is that this is time independent, and there's actually no energy exchange. So the axion can only sort of exchange energy. The only way the axion can couple is with zero energy. And since it's derivatively coupled, it has zero energy, it has zero momentum, and there's no coupling. So in this limit that we talked about is a symmetry limit. The axion just doesn't couple. Okay, so there we're predicting something falling through kind of the consequences of symmetry on this effective field theory. We're predicting something about how axions couple to the nucleons. So if you look sort of through the possible processes that you could have, you could have two nucleons in a 3s1 state, try to produce an axion, and that actually vanishes irrespective of the scattering lengths, because you're coupling here to spin. And that is always a good charge of the non-relativistic theory. But there is a way that you could have the process go where you switch from a 1s0 state to a 3s1 state. And this guy vanishes if the scattering lengths go to infinity. So if you ignored what I just said and you ignored this here and you just went ahead and calculated the Feynman diagrams, you would just find that the amplitude to this thing is proportional to this kind of factor that we saw before. And since the scattering lengths are large, it's vanishing if the scattering lengths go to infinity. Okay? So at lowest order in the effective theory, it's suppressed, this process, and that has implications for, of course, the phenomenology. You could also put in higher dimension operators like the C2s. Then, of course, you can get a contribution, but that's higher order in the power counting, and that affects how the axion can be constrained in the sun. Okay, so that gives you a little bit of feeling for what you can do with this effective field theory and how you can kind of exploit symmetry as well as the calculability of the effective theory to make lots of interesting predictions. Okay, so any questions about that? All right, so that's all I have to say about that effective theory.